Good afternoon. Hello. We are going to do 7-2 today, and 7-2 is all about similarity transformations. So we just kind of have to remember what our transformations are. Things that are included in transformations are rotations, reflections, translations, which are the slide, and now dilations. Okay, so we have those 4 transformations. So this is just saying if I can, move one shape onto another using those transformations, then those shapes are similar. So 3 objectives for today. We are going to skip around a little bit, but our 3 objectives are to understand that two figures are similar if there is a similarity transformation that maps one figure to the other. So like I said, if I can take one figure and transform it onto the other, right? If they line up, then the two shapes are similar. Then we're going to identify a combination of rigid motions and dilations that maps one figure to the other. And then we're going to identify the coordinates of an image under a similarity transformation. So we have a new vocabulary term today, which is similarity transformation. And then we're also going to look at properties of similarity transformations. So both of these are going to be in the back of your packet. So let's go ahead to that terms page and find our vocab for today, which is similarity transformations. Okay, so here we are on the terms page, and our new vocab for today is similarity transformation. So this is a composition of one or more rigid motions and dilations, a transformation that preserves shape but not size. All this means is same shape, different size. So just a quick way to, to remember this. We just have same shape, different size. So if two figures are the same shape but different sizes, we say that they are similar. Okay, so if I have triangle, right, A, B, C, I can translate it and dilate it. So I can slide it over here to the right, and I can dilate it by making it bigger to A prime, B prime, C prime. So these two triangles are the same shape, they're just different size. Okay, so if I had like a regular hexagon and then another regular hexagon, right? Same shape, different size. So the next thing we're going to look at is the properties of these, okay? So when you have, sorry, my dog wants to be in the video. When you have similar shapes, right, all angles are preserved, and sides are proportional. Okay, so let's draw a diagram here of what this means. So if I have that triangle, let's just do ABC again. A, B, C. And I translate it and dilate it. Something like this. A prime, B prime, C prime. Okay, so in order for these two shapes to be similar, all the angles have to be similar, or the corresponding angles have to be the same. So A and A have to be the same angle, right? B and B and B prime have to be the same angle. And then C and C prime have to be the same angle. So that's what we mean by angles are preserved. The angles don't change. And then the side lengths have to be proportional, meaning they all multiply by the same number. So if this is like 3, 4, and 5, let's just say, making up numbers here, right? 3, 4, and 5, then in order for this triangle to be similar, I would have to multiply by the same number to all three of these sides. So let's say that I dilate it by a scale factor of 2. So then I would have 3 times 2, which is 6, 4 times 2, which is 8, 5 times 2, which is 10, right? And then that would tell me that the scale factor is 2 because I multiply all 3 sides by 2 to get the new triangle. So angles are going to be the same. Sides are proportional. Okay, and that's just the property of similar shapes. Let's go back then to 7.2 and see how we use these properties. Okay, so here we are back at 7.2. Let's look at example 1. It says if line M is represented by the equation x equals -3, what is the graph of the image of triangle ABC dilated by a factor of 0.5 and then reflected over line M? Okay, so let's look at a couple things here. One, let's draw line M. It's x equals -3, so it is going to be a vertical line because it's x equals. So here's line M. Okay, and remember that when we do these transformations, we always do this guy first. So we always do the one that's to the right first. So this just means that I'm dilating everything by a scale factor of 1/2 or 0.5. So it's not as scary as it sounds, right? A is the 0.24. So then A prime, you just multiply both of these by 1/2. Remember that multiplying something by 1/2 is the same as dividing it by 2. So really I'm just dividing this by 2. So 2 divided by 2 is 1. 4 divided by 2 is 2. So A prime is at the 0.12. Okay. Then B is at the point -28. I'm multiplying it by 1/2, which is the same as dividing it by 2. So -2 divided by 2 is -1. 8 divided by 2 is 4. So -1, 4. And that is B prime. And then lastly, C is 0, 10. So I'm just going to multiply everything by 1/2 or divide by 2, C prime. 0 divided by 2 is 0. 10 divided by 2 is 5. So 0, 5. So here's C prime. And I can just connect them. Boom. So there's the dilation, right? Now we can do the reflection. So then you do the reflection second. And the reflection is just reflecting over this line M. So I'm just going to count to the line and then count past the line. So B prime is two coordinates to the line, so it's 2 coordinates past the line. Can't call it B prime because I already have that, so this is going to be B double prime. A is 1, 2, 3, 4 coordinates to, or 4 units to the left, so 1, 2, 3, 4. 4 units again, and that is A double prime. And then C is 1, 2, 3, so I count 1, 2, 3. Here's C double prime. So there is the graph, this guy right here. Okay, so we can say that a reflection with a dilation of 0.5 of triangle ABC equals triangle A double prime, B double prime, C double prime. Remember that you always do the one that's on the inside or on the right side first. So we dilated it by 0.5 by just multiplying everything by 0.5 or dividing by 2. And then we reflected it over line M. And that got us our new graph. Okay, next one is a try it. Let's scroll down. This one doesn't really fit on the graph, so do the best you can. But it says the vertices of XYZ are 3, 5, negative 1, 4, and 1, 7. What is the graph of the image XYZ translated to the right 1 down 2? So remember what that means. Right, to the right 1 and then down 2. And then dilated by a scale factor of 2. Remember, you do the translation first, then the dilation. Then what is the graph of image if I rotate it 90 degrees around the origin? So remember, because it's positive, we go counterclockwise. And then I'm dilating it by a scale factor of 3. So I'm going to multiply it by 3. Okay, I want you guys to try it. If you get it wrong, it's no big deal. That's why we work in pencil. But I do want you to try it. And then when you're ready to review it, just hit play. All right, guys, so hopefully you gave this a shot. Let's go ahead and look at part A here. I need to translate it right 1 and down 2 first. So watch what I'm going to do. I'm not going to graph it all the way. I'm just going to go right 1 down 2. Right 1 down 2, and right 1 down 2. Okay, so that is the translation part of my transformation. Then I want to dilate it by a scale factor of 2, right? So I've done this one first and then this one second. So I want to do a scale factor of 2. So what that means is right now I have a point. This point is at 0, 2. So I'm just going to write this down here. You don't have to write it down if you don't want. 0, 2. If I dilate it by a scale factor of 2, that means I just multiply both of these by 2. So 0 times 2 is 0, 2 times 2 is 4. So the actual point I'm looking for here is 0, 4. And I can get rid of this one. Okay, and this will be y prime. Okay, and now I'm going to do the same thing with my next point. This coordinate right now is at 4, 3. So if I dilate it by a scale factor of 2, it becomes 8, 6. So 5, 6, 7, 8, 5, 6, 8, 6 right there. And then that will be x prime. And I can get rid of this point. Okay, so hopefully that's making sense. I translated it first, and now I'm just multiplying the coordinates by 2. The last one here is at 2, 5. So if I dilate that by a scale factor of 2, I will get 4, 10. So 4, 10. And that is going to be z prime. Okay, and then the last thing is I can just, let's get rid of this point too so it's not confusing. There we go. Last thing I can do is just connect my points like so. And so now I can say that the dilation mixed with the translation of triangle XYZ, running out of room, so let's get rid of this, equals, triangle X prime Y prime Z prime. And that's it. Okay. The next one says, what is the graph of the image if I rotate it 90 degrees and then dilate it by a factor of 3? So I'm going to go ahead and erase this red one just so that we can kind of keep our facts straight, but I don't think that you should erase it on your paper. So I'm going to do this one in blue. Okay, so remember that rotating it 90 degrees around the origin, it goes counterclockwise. And so if you remember, all I do is I switch the X and Y coordinate, and then because this point is going into this into quadrant 2, the 7 will be negative. So negative 7, 1 is a point, is my Z. Now I have not done the dilation yet, right? So this is the point negative 7, 1. Now if I dilate that by a factor of 3, it becomes negative 21, 3, which like doesn't really fit, right? 1, 2, 3. Here's 10, 21, so I'll just label it here. Z prime is at the point negative 21, 3, and I'm estimating there. Okay, so there's Z prime, so I can get rid of all this stuff now. Now let's do the same thing for X. I'm going to switch the X and Y. Because it's going to go into quadrant 2, the 5 becomes negative. So negative 5, 3 is the point. And then if I dilate that by a scale factor of 3, it becomes negative 15, 9. So here's negative 10, negative 15, 9. And again, I'm kind of estimating here. So this will be X prime, and that's the point negative 15, 9. I can get rid of all this stuff now. Okay, and then the last one is Y. If I switch the X and Y, I get 4, negative 1. That's going to come down here into quadrant 3, so they're both going to be negative. And then dilating it by a scale factor of 3, that gets me negative 12, negative 3. So negative 12 is here, negative 3. So this would be Y prime, and that's the point negative 12, negative 3. And then I can connect those points. Oh gosh, I was really off on that. It's okay. Okay, so the dilation with a scale factor of 3, unioned with a rotation of 90 degrees around the origin of triangle X, Y, Z. And I just realized, right, we have to use double primes because we've already used primes. So all of these have to be double prime. That's okay. So this equals triangle X double prime, Y double prime, Z double prime. And there it is. So I know it doesn't really fit on the graph, but just to give you an understanding of what we did, right? We rotated the points 90 degrees, and then we multiplied the coordinates by 3. Okay, we have one more. Try it here for you. So let's scroll down. Here it says, what are the vertices of a rotation of 270 and then a dilation of 4 for triangle ABC? So go ahead and hit pause, try it, and then when you're ready to go over it, hit play. Okay, so there's a couple ways that we can think about the rotation, right? Because this is what I have to do first. So if I rotate it 270, that's rotating it three times of 90, right? Or I can think of it as rotating it negative 90, which is just going 90 degrees, but in the clockwise direction. So sometimes I think that that's a little bit easier to think about. Right, because if I have a clock, right, and here's like 12, right, 12, 3, 6, 9, we're thinking about a clock. If I go around 270 degrees, it gets me here. Well, if I go around 90 degrees, it gets me here. So I get to the same spot either way. Anyway, so if I want to rotate B, I don't know why I'm starting with B, but we are, it's at the point 3,5. To rotate this clockwise 90, I switch the X and Y, so it becomes 5, 3. And because that puts it down here in quadrant 4, the 3 will be negative. So 5, 1, 2, 3, right? Then it has a dilation of 4. That means I have to multiply the 5 by 4, which gets me 20, and the negative 3 by 4, which gets me negative 12. So that tells me that B prime, because it just asks what are the vertices, it doesn't ask me to graph it. So B prime is the coordinate 20, negative 12. Okay, now let's look at A. A is at the point negative 6, comma 4. To go 90 degrees, I would switch the X and Y. So 4, negative 6, which puts it into this quadrant. Well, this quadrant, everything's positive. So it will become 4, positive 6 in quadrant 1, right? Which is 4, 6 is right here. Then I multiply everything by 4. So that tells me that A prime is going to be the coordinate point. 4 times 4 is 16. 6 times 4 is 24. And that's it. Hopefully this is making sense how we're doing this. Last one is C. This is the point 2, comma 1. To rotate it negative 90 degrees, right? I switch the X and Y, so 1, comma 2. And that puts it down here in quadrant 4. Quadrant 4, the y coordinate is negative, so it'll be 1, negative 2. And then I multiply everything by 4. So 1 times 4 is 4. Negative 2 times 4 is negative 8. And that is it. I have found the vertices for all of my I have found the coordinates of all of my vertices for this triangle when it's been rotated 270 degrees counterclockwise or 90 degrees clockwise, it's the same, and been dilated by a scale of 4. So if that's not making sense to you, make sure that you reach out for help. We're actually going to skip example 2 and example 3 here, and we're going to continue on with example 4. Okay, so example 4 says, can the artist copy her sketch to cover an entire wall measuring 15 feet high by 20 feet wide, so her wall mural is similar to her sketch? Explain. Okay, so let's look at this. So currently I have this mural that is 14 inches by 11 inches, right? And I want to see if it will fit on a wall that is 15 feet and 20 feet. Now, so we can just do it, right? 15 feet, 20 feet. Now, I can't compare these right now because one of them is in inches and the other one's in feet. So what we're going to do is we're going to change this 15 feet to inches by just multiplying it by 12. So 15 times 12, 180. And then 20 times 12 is 240. Okay, so now because they're in the same units, I can compare. If this sketch is the same shape as the wall, then it'll fit perfectly. So I just need to see what is the scale factor. Remember, the scale factor is always the new side over the original side. Okay, so here my new side, I'm going to do 180 inches divided by 11 inches, which gets me like 16.3636 repeating. Okay, so the scale factor here is like 16.36 repeating. Now I want to find the scale factor for the other side, and it should be the same. It should be this 16.36. If it's not, then this sketch is not going to line up on the wall. So 240 divided by 14 gives me 17.143. So is the scale factor the same? Is this sketch going to line up on this wall perfectly? And the answer is no. It's not going to fit because the scale factor is not the same. So we can say no because the scale factors are different. Because the scale factors are different, I would have to multiply one side by 16.36 and the other side by 17.143, and I just can't do that. It has to be the same for both. Okay, so here it says then, suppose the artist cuts 2 inches from the width. Okay, so then that means now that her sketch is now 12 inches. Okay, how much would she have to cut from the height so that this will fit, right? So that it'll fit on the wall. So again, here's the wall, right? This is 240 inches, and this is 180. I don't know why I just put degrees. That's funny. Okay, so I want to know what is the scale factor then, right? So if I do my new side, 240 divided by 12, I get 20. So it has a scale factor of 20, right? The scale factor will have to be 20, which means that whatever x is, I would have to multiply that by 20 to get 180. So I can do it this way, 180 divided by x, right, has to also equal 20. So let's solve. We can multiply by x, and I get 180 equals 20x, divided by 20, divided by 20, and I get x is equal to 9. So this has to be 9 inches in order for her sketch to fit on the wall perfectly. So then the question is, how much would she have to cut from the height? Well, the original height was 11. It has to be 9, so she would have to cut 2 inches off. She would have to cut 2 inches off the height. And that's it. So again, hopefully you're kind of understanding how that works. We have one more try it for you guys. So let's clear this and keep looking. Okay, very, very similar. An art museum gift shop sells prints of a famous painting. The original painting is 120 centimeters wide and 85 centimeters tall. if the print is 20 centimeters wide, how tall is it? So again, it's all in the same unit, so we're good there. So you're just trying to find how tall is the print. So use the same method we did on the previous problem. Pause the video, give it a shot. When you're ready to go over it, hit play. All right, so hopefully you guys gave this a try. I have gone ahead and drawn the original painting and labeled it, and then the print and labeled it. Now, in order, right, the ratios have to be the same in order for these two shapes to be the same shape, just different sizes. So I can just set up a proportion. There's a lot of different ways that you can set this up, okay? So I can say 120 over 85 equals, if I do 120 over 85, I have to do 50 over x. And then I can just cross multiply and solve for x. That's one way. I could also have done 120 over 50. And if I did 120 first, I would have to do the 85 first. So 85 over x, that's another way. You also could have done the reciprocals of those. Okay, so there's lots of different ways to have done this. I'm going to go ahead and just stick with this way because it was the first one I wrote down, but it doesn't matter. You should get the same answer either way. So when I cross multiply, I get 120x equals 50 times 85 is 4250. Just make sure that's right. Yep, 4250. I'm going to divide both sides by 120. And I get x is equal to 35.42 centimeters. So that is how tall the print is. Okay. We are almost done. We just have 2 proofs left. So we're going to do example 5. Excuse me. Example 5 says identify similar circles. Write a proof that any 2 circles are similar. So any 2 circles I want. Okay. So let's just say given a circle P, so there's one circle. You always label the center with the name, so circle P with radius R. And then given another circle, so circle Q with radius S. And I want to prove that these 2 shapes are similar. So remember, similar means same shape, different size. So how do I prove that 2 circles are the same shape? Okay, and it doesn't say it has to be a 2-column proof or anything, so we're just going to write down the words. Okay, so we're going to translate P to Q. So what that means is we're going to slide circle P over so that P and Q are lined up perfectly on each other. So then you don't have to draw this, it'll look something like this, right? Where this is S and this is R. And this is P and Q. So I'm just moving this circle over to line up with that circle. Okay? So I know the centers are in the same spot. Then we can find a scale factor that dilates, so makes bigger or smaller, circle P. So P is going to get either bigger or smaller so that my radius, that radius R is equal to my radius S. So if P and Q are in the same spot and R and S are the same, the radius is the same, then the circles are congruent, right? So we can say since there is a composition of rigid motions, So since I was able to use translation, reflection, rotation, dilation, right? So rigid motions and dilations, that allows circle P to be congruent to circle Q. So since I can make circle P and circle Q exactly the same using dilations, then that tells me that at the moment how they are similar. And this symbol right here without the equal sign means similar. With the equal sign means congruent. Okay, so at the moment I can say that circle P and circle S are the same shape, but just different sizes, which makes sense, right? We know circles are the same shape and different sizes. Okay, you guys are going to use almost like identical concept, right? This exact same concept to try a proof about squares. Oops, let me clear. Why won't it let me clear? That's weird. Here we go. Okay. So we're going to use pretty much the exact same idea to prove that two squares are the same. So again, if I have, let me draw it a little bit further down. If I have a square, A, B, C, D, right, with side length R, and then I have another square that is E, F, G, H with side length S. Okay, prove that these two squares are similar. So we want to prove that they are the same shape but different size. So go ahead and hit pause, use the exact same concept that we did on the previous problem and see if you can get this one. Okay, so let's go over this. This is what I have. I said I'm going to translate A to E. So I want this corner and this corner to line up perfectly. Then I'm going to figure out a scale factor and so that R and S are the same length. So if this is now also A, right, and then this is S and R, and this is A, this is B, this is C, and this is D. And they line up perfectly on each other. So since I'm able to do that, since a similarity transformation exists, since I'm able to take A, B, C, D and translate it and dilate it so that it fits in E, F, G, H, then I know that these shapes are similar. Again, similar just means same shape, different size. Okay, that is it for 7-2, you guys. Nice job. If you have any questions with this, make sure you reach out. I know that some of these ideas are a little bit more abstract. So again, make sure that you reach out if you need any help, and we'll see you later.